So in this video we're going to come up with or derive the arc length formula when we're working with polar equations. And the big tool we're going to use is the fact that we've already come up with a parametric formula for arc length if we have parameterized curves. So if we have x and y parameterized via some other parameter t, then we know that we can calculate the arc length by running over the t interval of interest by taking the square root of the sum of the squares of the derivatives of the parameterizations. So the idea is we know that if we have an equation in polar form, so where we're describing the radius as some function of theta, this is a polar equation. And if we're interested in finding the arc length of some curve, as we move from a radial line that hits the line in the ordered pair r naught, theta naught, and another radial line, say, that hits at a point r sub 1, theta sub 1, if we're interested in finding the length of the arc as we move from theta naught to theta sub 1, what we can take advantage of is the fact that we know how to parameterize the polar form of an equation, because in trigonometry we learned that x is equal to the radius times the cosine of the angle theta. And because the radius is being described as a function of theta when we're working in polar form, this gives us x as a function of theta. So this is a parameterization of x in terms of the variable theta. And we also know from trigonometry that y is equal to r times the sine of theta. But because r is a function of theta, this makes y a function of theta. So we have a parameterized curve. So to get the arc length, we're going to need to take x prime of theta and square it and add it to y prime of theta and square it. So we have this stuff that's going to need to go under the radical sign. And what you usually want to do is clean it up by doing scratch work before you cram it under the radical, so you're not dragging everything along with you. So if we think about doing x prime plus y prime, that's just going to be a matter of taking the derivative of x and y right here. So this is going to be a product rule. Because r is a function of theta, we would need to use the product rule. Radius isn't a constant. So we would say by the product rule we would get r prime, and then it would be times the cosine of theta, and then we would get plus, and then we would get r times the derivative of the cosine. But the derivative of cosine is minus sine, so here we would get minus sine theta, plus then we would need the derivative y prime. So we're going to take the derivative of the radius r prime, times the sine of theta, plus, by the product rule, r times the derivative of the sine, which is the cosine of theta. And we know underneath the radical sign we're going to need to have the sum of the squares, so we know we're going to need to square each derivative and take the sum to figure out what goes under the radical sign. So this needs to be squared, and this derivative here needs to be squared. So when we square, we know it's going to be first term times itself. So r prime cosine theta times r prime cosine theta is going to be r prime squared times the cosine squared of theta. And then we get r prime cosine theta times minus r sine theta twice. So we get minus 2 times r prime r sine theta cosine theta. And then we multiply minus r sine theta times itself, which is going to give us plus r squared sine squared of theta. Then plus, from here, we're going to need to add the squaring of this. So when we square this, we're going to get r prime sine theta times r prime sine theta is r prime squared times sine squared of theta. And then we're going to get r prime sine theta times r cosine theta 2 times. So we're going to get plus 2r prime r sine theta cos theta. And then we'll get r cosine theta times itself. So we get plus r squared cosine squared of theta. And what we want to notice is that the middle term right here cancels with the middle term right here. They're opposites, so they will give us a 0 when we add them together. And all that leaves us is adding these two terms. But notice each term here has an r prime squared in it. So when we add them, we can factor the r prime squared out. And what will be left on the inside will be a cosine squared of theta plus a sine squared of theta. And then here we have a plus and a plus, but the r squared term shows up in both of them, so we can factor the r squared off, which will leave us with sine squared plus cosine squared. And then those are just our Pythagorean identities, so we know that this is equal to 1, and this by the Pythagorean identity is equal to 1, so we get r prime squared times 1 is just r prime squared plus r squared times 1 is just r squared. So this is what gets to go underneath the radical sign. So now we can calculate the arc length. We can say the arc length is going to equal, the parameterization is running from theta naught to theta sub 1. And then we want theta naught to theta sub 1. And it's going to be the square root of the r prime being squared plus the r squared term, d theta, because we're parameterizing with respect to theta. And we could just as easily replace the r and the r prime because r is equal to f. We could f of theta, we could replace r in the formula with f of theta, and we could replace r prime with f prime of theta, which is a common way to see it. And so if we did that, it would just look like this. We'd get theta naught to theta sub 1 of the square root. We'd have f prime of theta being squared plus f of theta being squared, and it would still be d theta. So the next slide just summarizes that, where I'm letting if we let alpha be theta naught and we let beta be theta sub 1, then it comes in a form that's more common in a textbook. Run it over the interval from alpha to beta, and then take the sum of the squares of the function and the derivative of the function, or the radius and the derivative of the radius.